In this section, we are going to solve another example on floating point system. And here we have the question: place the given number into n-digit floating point format for the given value of n. Calculate the relative error, then use the result to determine the number of significant digits in the approximation. And we're given two examples here to be done. So at first, what we're supposed to do to this is convert this into floating point format. So here we have the number written, and we have to convert this into the floating point format. So this in the floating point format will be 4 point. So we have one non-zero digit in front, and then the rest, so 5, 6, 7, 1, 2, 3, 4, 5 times 10 to the power, since the decimal has moved 1, 2, 3, 4, and 5 steps. So we have 10 to the power minus 16 now. And now we have to place this number here to n digits. So we'll just take n significant figures from here. That would be 4.56712. Okay, until 1. No, sorry, 6 digits, so until 2. Yeah. Times 10 to the power minus 16. So now we have placed the number into n-digit floating point format here. And what we're supposed to do next is finding out the relative error. Which will be the original value, which is 0.00045671234 5 times 10 to the power minus 11 minus the approximated value, which is 4.56712 times 10 to the power minus 16 divided by the original value, which is again 0.00045671234 times 10 to the power minus 11. And this gives us the relative error as 7.55 times 10 to the power minus 7. So the question asks us to determine the number of significant digits in the approximation. So that we can do it from the relative error here. So the 10 to the power, it's minus 7. So we just take the 7, the integer value, and we can say that the number of digit approximation is 7. Now going on to the second example, we have here that's 18.9123456 times 10 to the power 6, and the value of n is equal to 4. So first we put this number as a floating point number, 9123456 times 10 to the power 6. and that would be after one non-zero digit the decimal, so it would be 1.89123456 times 10 to the power 7. Now using the n is equal to 4, so we only take 4 significant digits here, so we have 1.891 times 10 to the power 7, and then the relative error is equal to the original value minus the approximated value, that's 1.891 times 10 to the power 7 divided by the original value, which is 18.912345.10 times 10 to the power 6, and this gives us the value 0.0001240248. So that converting that into the floating point number would be 1.240248 times 10 to the power. So the decimal goes like 4 steps. That would be minus 4. So we can say here the number of digit approximation is 4. The number of digit approximation is 4.